All right, thank you. So I'm going to switch gears a little bit. All the great science talks yesterday, just hearing from Jack, and talk about the construction, the architecture, some considerations for a lunar base. And what I'd like you to take away from this talk today is not necessarily the specific design and way to build this base, but rather some considerations that we need to take into account now, early on, in order to defend ourselves from a suboptimal solution in the future. This is a study that we're conducting at JPL, but I'm sure you'll recognize many of the names on the screen here, including Tony Colapri, Terry Fong from Ames. Many of them are in the room today. Our industry partners at Honeybee and Ceres Robotics, Phil Metzger at UCF, and of course, Jack and Sandy Magnus, our astronaut representatives. So I know you're probably thinking, what's the two? So let me start by taking you back to the 20-year anniversary of Apollo 11. Back in 1989, NASA Ames ordered the first RLSO. This was conducted by Boeing, and they asked them to develop a concept for a lunar base that could be constructed robotically and attended later by humans. This base would produce liquid oxygen. This was a little bit different than what we're looking at now. It was located on the near side. They used reduction of ilmenite to produce the oxygen, but regardless, the study came up with a few conclusions that are important even today. Those conclusions are up on the screen now. The first is the importance of integrated element designs. With something as complicated as a lunar base, focusing on one or another subset of ideas is going to guarantee suboptimal results. You can't have a lander without a robot designed to take things off the lander. They need to be designed together. The second is quantified operations analysis. With something like a base, a very small change to something that might seem very simple is going to have ripple effects that go through the entire system. And those things need to be taken into account early on, and they need to be modeled so that you can analyze those ripple effects and assess the entire base architecture. These two things, even though they were discovered 30 years ago as part of this report, are critical to our current study today, and you'll see that they're baked into that whole, to some of our current results that I'll show you. So we asked ourselves, with the 50-year anniversary of Apollo 11, what would RLSO look like today? Obviously, we know a lot more after 30 years. We know that at the poles, there's volatiles, including water ice. We have experience from the ISS, different international collaboration opportunities, new flight systems, Orion, SLS, Gateway, and new tools. When we have CAD now, we have spreadsheets. These were all things that didn't exist 30 years ago, so we can do this study better today. So before I get into some specific results of the current study and some ideas that we have, let me bring you back to this idea of quantified operations modeling. This is critical, and this is the bread and butter of the entire study. We have broken up the base into the 4 elements that you see on the flow chart above. All of these are interconnected. Each of those blue boxes involves many different sub-elements, but the point is that changing one parameter that seems small in the lander, for instance, is going to ripple through to everything else. We've created an operations model that takes all of this into account, the connectedness of these elements. We have populated that model with some initial assumptions and ideas, but the important thing is that we've made this expandable from the start. If we want to look at a lunar base at the South Pole with 4 flights a year, 30 days each for astronaut excursions, we can do that. If you want to look at the exportation of propellant for a Mars flight every 2 years, you can do that. These are all parameters that can be changed, but they allow us to analyze how those different base architectures will affect the entire system. So I'm going to show you some numerical results of the model that we have right now, but the point that I want to get across is that this is a flexible tool that we want to continue to use in today's lunar environment. Okay, so let me dive into some of those blue boxes into a little bit more detail. The first one is the ISRU. As I mentioned, we are focused on water ice at the South Pole. This is probably not new information that the Lunar ISRU workshop that happened last week, there was lots of discussion about this. But we've broken this up into 6 fundamental steps in order to produce propellant. These steps can be combined. Some methods put excavation and extraction together. For instance, Chris Sackney presented on PVEX, the coring drill system that extracts volatiles in situ. But these 6 steps are fundamental no matter where you put them all within the base architecture, and our model takes all of that into account. Also important is understanding the different pieces of the base. The pictures that you see on the right are some of our current ideas for these designs. They're not necessarily the best way to do it. They're not the only way to do it, but they're a good starting point. And as we continue to advance and create this architecture, we can bring in other people's designs and assess how they will affect the entire system. Obviously, we're going to need an energy system. The ISRU especially is incredibly energy intensive, and I'll show you some numbers that show how intensive that is. We need a habitat for the astronauts. It needs to be shielded. We need all the different ISRU systems for mining, extraction, processing, and finally we need a lander. And the lander that we've designed is a single-stage reusable lander. To put this in a different perspective, I have this picture which kind of shows the scale of our current designs. As you can see, we have a shielded habitat with an expandable tunnel that is covered by regolith to prevent having to bury it and simplify operations. We have this lander, we have this mobile gantry system that can go over the lander, pick things up, it can then go into the tunnel and inspect and maintain the habitat. And this is where I bring up again the importance of the integrated design of all of these pieces. The gantry needs to be developed with the lander and the tunnel in order for them all to work together. And no matter where we go in the future with the base architecture and different international collaborations and commercial partnerships, we need to take that integrated philosophy of all of the design elements into account early, or else we're going to end up with things that won't work together. Also important, because ISRU is so critical to the steady state operations of our base, is coming up with some assumptions for the resources. This was put together by Tony Colapret here at Ames. These are our initial assumptions of defensible resource estimates, recognizing that, of course, we need a prospecting mission to help to nail these down. Tony put this together using the tools that he has. We've broken this into 4 resource types, one of which has a subtype. Type 1 is kind of the typical PSR, where we estimate that you'd have about 2% water weight in the regolith. There's some thoughts of a very thin surface frost. That's the type 1B. Type 2 and type 3 are areas that are not permanently shadowed and have different water weight percentage at different depths. We're focusing for our current study on type 1A and type 2. While the surface frost may be present, it's just so thin that it's not very useful for a production scale ISRU environment. And type 3, the resource at only 0.5% is just so small that it makes it very difficult to actually use that. But once again, I'll mention that what this really comes down to is the creation of that model, and that percentage number and the depth number is an input to the model. And as we learn more, we can change that and we can see how that affects things. Okay, so given all of this, we've come up with 3 kind of broad architectures for the purpose of drawing some comparisons and some conclusions. The first one here is kind of a very typical base that you'll see very often. In this, we're at Shackleton crater. Everything is located down in the crater in the PSR, where we have the greatest resource, except for our energy system, which is located up along the rim in the persistently lit regions. In this architecture, we're using laser power beaming down into the crater. With mining rovers that go grab regolith, they bring it back to the base where you extract the volatiles, you spin them into propellant. Option 2 is kind of similar. We're still at Shackleton, but in this case, we've moved things up and out of the crater. We're still mining within the crater, but we've moved all the base elements and the ISRU processing up close to the energy system, which decreases the losses that you'll see in transporting that energy. The challenge here is now you have to bring resource up and out. So there's no easy answer, but the point is to compare these architectures and start to decide which one seems to make the most sense. Option 3, we're still at the South Pole, but you can see from the picture to the left, we've now moved to the ridge of Shackleton. There's these ice fields where the resource is not as useful. It's only what we'd estimate to be 1% water weight. But everything is much more co-located now. You don't have to deal with crawling in and out of Shackleton. So this is kind of an example of something that might initially seem suboptimal because you aren't in the PSR, but might actually make the most sense because of other implications involved with the architecture. So I'll show you some results of our current modeling to kind of compare these things. But the point is to consider these and start to make some decisions about what makes the most sense and with quantified results. Okay, so let's get into some numbers just to kind of bound your thinking. So as I mentioned, our current lander is a single-stage lander. Starts at the base, goes up to Gateway, grabs astronaut and cargo, comes back down. One flight of that lander requires about 40 tons of propellant, which means that you need about 50 tons of water because the engines burn at a mixture ratio of 6 to 1. We assume that we're running our ISRU at half-time operations. That's a pretty good assumption for now. That means you need about 1,000 kilograms of water per day. It's a lot. Using the estimates for regolith that I had from the other slide, we can see that you need a lot of regolith, approaching 1/4 to 500,000 kilograms. You're not going to go out with your shovel and get this. If we look at the base energy needs, you can see that ISRU dominates the base, and beyond that, the electrolysis portion of ISRU is about half of the entire base energy needs. These are the types of results that we need to start to make now because we can start to analyze what makes the most sense to optimize and develop in terms of technologies. If electrolysis is going to be the biggest energy need, perhaps that's what we should be working on right now to improve. We can also compare energy need across the different base architectures. I showed you those three. So what we can see here is option 1, where we're in the PSR, requires significantly more power, and that's because you need to get all that power into the crater. Power beaming is very inefficient, so because of that, you need a much larger power source. Whereas option 2 and option 3, where the base is located closer to the energy system, you don't deal with such large losses. So even though the best resource might be in the PSR, maybe that's not the best place to actually put your base because of other implications involved. So here's kind of a very simple option comparison in terms of the ISRU, the base architecture. But I've also highlighted in red some things that are very relevant to our discussion here, and that's the exploration side of this base. Even though the PSR may be the best in terms of the resource, it's dark and it's hard to explore from that location. So maybe it doesn't make sense to go there. Maybe we want to put the base in that lit area and then deal with the other implications that come from that in terms of the ISRU. So finally, I'll leave you with some emergent findings, and this has come up throughout the course of this talk. The best ice resource may not be in the PSR. It may be it may be in other locations. Nuclear power, something that's discussed very often, while useful. For production scale ISRU, it's going to need to be megawatt class. We need a lot of power. And finally, these are things that have come up in our discussions, but what the model allows us to do is we have to make a lot of assumptions on the inputs. But when we make all those assumptions, then that immediately tells us what we need to go find to fix those assumptions and to come up with better estimates. And some of those are listed here, and these would be excellent opportunities for CLIPS payloads and missions in the future to help to do some prospecting and dial in some of these assumptions so we can make better decisions. So thank you.
We have 2 minutes for questions.
Okay. All right. So let me ask a difficult question here.
Sure.
Essentially, everything you've shown me here shows how really, really difficult this is going to be.
Mm-hmm.
And difficult equals expensive, right?
Sure.
So at what point do you look at all this and say, this is not realistic, it's not going to happen?
That is not a decision for me to make. And you're completely right. This is difficult. It is hard. It is going to be, in my opinion, the crowning of human achievement if we can do it. But that being said, what we're focused on for this study is taking a realistic look at it, a quantified look that's tractable and defensible with assumptions that we can stand behind. So I show you these numbers today not to scare you, but so that we can think reasonably about it. And going forward, we can continue to use these tools that we've created to make some of these decisions and find out what is best for everyone.
Yeah. And don't get me wrong, I absolutely think we should be doing this. We should be doing a lot more of this. But I think the question has to be asked whether, is this ever going to happen in any kind of realistic architecture that Congress is going to fund? Okay. I think that has to be asked because I don't think that question is being asked.
I agree with you.
Okay.
One more question? Go ahead, Paul.
Yeah, let me make a pitch for more orbital remote sensing. We obviously we need to get on the surface and see what some typical or useful location looks like. But we can make huge improvements in what we know from additional orbital remote sensing, high resolution hydrogen maps. We can measure the abundance of surface ice and link those to processes down to a few ppm, tens of ppm at sub-100 meter scale. So there's a lot we can do with small satellites that can fill in a lot of blanks and really bring the geologic predictability of where ice might be at the surface. So there's some low-hanging fruit from orbit.
Thanks, yeah, I agree. And as we get more of that information, I'd like to see us continue this type of analysis to see how that affects everything. Yeah. Thank you.